Got it? All right, I will begin with a word of prayer. Again. Heavenly Father, we thank you for today. Again, Lord, I just pray that you bless this class, help us to glorify you in what we do here, and I just pray you give us clarity of thought in what time remains, Lord. In your name I pray. Amen. I guess I'll just run through, I should always bring a light to plug in, you know? I think I'm preparing for class. It's not on my list, but maybe it should be. I guess I've got a phone, that's true. Okay, so let me just briefly run through. I'm not going to write, I'll just say in words how you do these. This one's telescoping. You do partial fractions on this, it will become clear how to find the nth partial sum. This one's geometric. The answer is 3 divided by 1 minus 1/10. This one is also geometric in reverse. I said I wasn't going to write. I guess I'll write. So this is equal to the sum x times minus 4x squared to the k equals 0 to infinity. And then you clean it up. So minus 4 to the k, x to the 2k plus 1, k equals 0 to infinity. That's that one. This one here diverges by the kth term test because minus 5 to the k over 4 to the k plus 1 diverges as k goes to infinity, does not go to 0. So this diverges by the kth term test. This one morally is essentially k over, I have to think about this one for a second. This is like k over k cubed to the 1/2 power, which is what? K over k to the 3/2 power, which is what? 1 over k to the 1/2 power? This thing diverges. So you ought to be able to show this diverges by limit comparison to the 1 over the square root function is one way. There may be other ways, but you can show this diverges. This converges. You could apply the integral test because you can make a u equals inverse tangent substitution, I think. You could also, I believe, I'm not 100% sure about this, but you could limit compare this to the p equals 2 series. I'm actually a little bit weary about the pi over 2 coming from there, but I think this converges. I'd have to work on it. What do you guys get for this one? Converges by limit comparison. By p equals 2?
That's one way to do it.
It's not p equals 2 though. What do you mean?
In your notes you did p equals 2.
This is not a p equals 2 series though. I mean, so what I'm saying is I could say
It like simplifies out. You compared it. Yeah.
I did? Oh, man, I forgot I did that. Well, you guys are lucky. Good. I don't have a very good memory. Let's see here. So this is what? This is less than or equal to inverse tangent, right? Of k over k squared. And, oh yeah, fine. So that's less than or equal to pi over 2 over k squared, which this converges, so that converges, and this is also positive. So, yeah. Direct comparison, I suppose you could do that. I think the book intends an integral test there, actually, when I look at it now. But whatever. Anyway, so there you go. I will try to write up a more formal solution for you guys, of course, but that's basically it. Okay, so next section, section 12.4, is on the root and ratio test. I will begin with the ratio test. Here's the ratio test. If you have a series with positive terms, all right, in other words, the a sub k are positive, is greater than 0. If you look at the quotient of the k plus 1th to the k term, and it goes to lambda. So lambda is some real number, all right? If that quotient, if that lambda is less than 1, it's a convergent series. If the lambda is greater than 1, it's a divergent series. If lambda is equal to 1, the ratio test says nothing. It's inconclusive, all right? So, I mean, all that it really tells us if lambda equals 1 is you got to try something else. All right, it's kind of like when you're working a limit and you work the limit out and you find out that, it's got form 0 over 0, that doesn't mean you get to cancel the zeros. You got to do something else, right? It's indeterminate. So if you get lambda equals 1, it just means that the ratio test is not the right tool for the job. You got to try something else. So here's the proof. If you have the ratio goes to 1, goes to lambda, which is less than 1, you can choose a mu between lambda and 1. All right? So we're assuming that this quotient goes to lambda. That means that there exists some constant, some integer k naught, so that whenever you're beyond that integer k naught, you have that a sub k plus 1 over a sub k is less than mu. I don't know if that's immediately obvious to you, but if it's tending, right? Maybe a picture helps with that idea. So here, you're tending to lambda. You've got mu in here, 0's down here, and so let's say b sub k is equal to a sub k plus 1 over a sub k for the sake of illustration. So maybe b1 is down here, maybe b2 is down here, maybe b3 is, I don't know why I'm drawing them like a graph. I mean, this is, sorry, I'm an idiot. There's a number line here, right? Okay, so maybe b1's here, maybe b2 here is whatever. Eventually, you get to some k naught, so that all of the things are closer and closer to lambda, right? So if you go far enough out, you should have all of the terms I'm confused all of a sudden. Oh, I'm an idiot. If the number line's going up, why is my picture wrong? Lambda less than mu. Which one comes first if I'm going? So that explains my confusion. All right. Now one is up here somewhere. The point is, if you're approaching lambda, right? Then if you go far enough up, you can definitely get all of the values less than mu, which is the claim here. It's pretty geometrically clear that you can do that once you don't draw number lines backwards. Sorry about that. Anyway, so once you've convinced yourself that this is reasonable, then you multiply a sub k naught to the other side. That is a sub k naught plus 1 is less than mu times a sub k. And then you just keep doing this, right? So that means a sub k naught plus 2 is less than mu squared times a sub k naught, just recursing this, and so forth. A sub k naught plus j is less than or equal to mu to the power j, a sub k naught. So you just keep going and going. Then if you look at any k larger than k naught, you can rewrite a sub k as mu sub k minus k naught. So here the j is equal to k minus k naught, right? And that's really nice because I can rewrite that as a sub k naught over mu to the k naught power. This is ugly, but it's a fixed particular number based on the limit existing. All right, this doesn't have a k dependence. It just has a k naught dependence. K naught is given to us by the existence of the limit. And so we get that a sub k is smaller than this term. But you can calculate the series that arises from this term is a sub k naught over mu to the k power k naught over times mu sub k. Pull out this constant, it's just a constant. And then you've got this series, which is the sum of mu to the power k, where mu is less than 1. Mu is a fixed positive constant less than 1. This is what? This is a geometric series. So we know that converges. Consequently, by the direct comparison test, we get that converges as well. So that's the proof of the convergent case. Now the proof of the divergent case is similar, but I won't go through it. Any questions? I mean, I wanted to. The proof of the root test is also based on the geometric series. I'll let you read that in the book. If you want to see me talk about it, you can watch last year's videos. I talk about it for longer than I should. I'm going to show you examples now, if that's all right. Okay, so I should probably state the root test, though. First, I'm going to show you an example of the ratio test. So let's see here. How about this? The sum 2 to the n over n factorial. Oh, I'm sorry. I try to use k in here, don't I? 2 to the k over k factorial. I'm going to do the next example in n just for a change of pace. K equals 0 to infinity. This makes sense because remember 0 factorial is not 0, it's what? It's 1, right? So here we have a sub k equals to 2 to the k over k factorial. Clearly that's positive, so we can apply the ratio test. Now we got to calculate the ratio. What's a sub k plus 1 over a sub k? What's that equal to? Do you guys understand what I just did there? What did I do here? I'm asking if you understand. Why? What did I do? I multiplied by the reciprocal, right? So to divide a sub k, I can multiply by 2 to the k over k factorial. In other words, the 1 over k factorial in the denominator flips upstairs, right? So pragmatically speaking, this is the way to calculate the ratio. Multiply by the reciprocal. I mean, you can write a fraction of fractions if you want, but eventually you're going to get back to this. So you might as well just write what's logical from the start. Less likely to make a mistake if you do it right. All right, now we got to do some simplification here. So this is 2 to the power k times 2, right, times k factorial. And k factorial is k plus 1 times k factorial by the definition of the factorial. And then that's all, of course, times 2 to the power k. We get some cancellations, all right? So, again, this is an identity for the factorial function, right? In fact, that's how I define the factorial. K plus 1 is k plus 1 times the k factorial, right? Anyway, so you see what cancels? This guy and that guy, right? And also, this one and that one, what are we left with? 2 over k plus 1. Right. So what's this go to? This goes to 0, right? Is 0 less than 1? Yep. So therefore, the sum k equals 0 to infinity of 2 to the k over k factorial converges. Any questions? Comments? Concerns? Yeah?
Can you go over how you got the 8 by 30 over the 2 to the power k over that?
How did I get the what? This? Well, this is equal to 2 to the k plus 1 over k plus 1 factorial big fraction, 2 to the k divided by k factorial, right? This is equal to 2 to the k plus 1 over k plus 1 factorial times k factorial times 2 to the k. I just write this directly because anytime I'm anytime I'm dividing by a sub k, that's the same as multiplying by the reciprocal of a sub k. So the reciprocal of a sub k is just formed by flipping the fraction that defines a sub k. So, yeah.
And where did the second k factorial come from in the bottom, in the denominator? Is it because k plus 1?
So k plus 1 factorial is by definition k plus 1 times k factorial. You know. If I had for example, if I had k plus 3 factorial, I could simplify this to k plus 3 times k plus 2 times k plus 1 times k factorial. As another example of this sort of algebra. These are games we can play. We may or may not need to play that game, but that's an identity which is known for the factorial, yeah. Another example of the ratio test, and I shortchanged the ratio test a little bit here because we do so much ratio test later on when we get to power series. It's like our main tool. So we'll do lots more ratio tests a little bit later in the course. So I'm just going to do a couple here. But here's another example. I'll do that n this time. Sum n equals 1 to infinity of, say, n to the n over n factorial. All right. Oh no, who will win? All right, so here a sub n is n to the n over n factorial. So I calculate a sub n plus 1 over a sub n. Here n is playing the role of k, all right? This is clearly positive for n greater than 1, so I can apply the ratio test, right? And so I'm going to use my algebra trick again. This is n plus 1 to the n plus 1 divided by n plus 1 factorial times the reciprocal of the denominator, which is n factorial over n to the n. So we use laws of algebra here. N plus 1 to the n plus 1 is really n plus 1 to the n times n plus 1, right? And then n factorial, well, that's just there. Downstairs, I have n plus 1 times n factorial using the factorial definition again, and then times n to the n. Well, we do get some cancellations here, don't we? We get this guy canceling, and also the n factorials cancel, right? So what we have is n plus 1 to the power n divided by n to the n. All right. Can you simplify that? Yeah, I think we can. So this is really n plus 1 divided by n, all to the power n, also known as 1 plus 1 over n to the power n. Well, that looks familiar. We know what that does. That goes to e. We've worked this out before as n goes to infinity, right? E is 2.71, blah, 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 blah. The point is it's a number, it's larger than 1, right? So therefore what? Yeah, therefore the sum n equals 1 to infinity of n to the n over n factorial diverges. By almost the same calculation, what could you say about the sum n equals 1 to infinity of n factorial over n to the n? So here I'm replacing a sub n with 1 over a sub n, right? It's almost the same calculation. It flips over, right? So I'm pretty sure that converges. Yeah. I leave the details to you. Similar calculation, though. Yeah. So basically, the moral of this story is that n to the n wins, right? In a battle of n factorial versus n to the n, you should bet on n to the n, right? N to the n wins. It's like way bigger. Okay. Although the factorial is no slouch. I mean, you know, put up a factorial against an exponential, it's going to win. Okay, so the root test is the following. Again, a series with positive terms. If you have a sub k to the 1 over k, the kth root of it, if that goes to rho, then 1, if rho is less than 1, that implies that the series converges. 2, if rho is greater than 1, then that implies that the series diverges. And of course, here we're looking at the slightly more careful statement of this is on page 593 of your book. But that's basically it. This is the root test. If you can, so here's an example, pretty typical example. You can kind of see, like when you see an example that's intending the root test, it kind of sticks out. So here's one. Like once you see it, you'll be like, oh, that's root test. 1 over natural log of k to the k power. It's like, oh, look at that. It's a k power. So let's say k equals 2 to infinity to keep out of trouble. K equals 1 is not advised here. Right? Log of 1. Uh-oh. So here, a sub k to the 1 over k is equal to 1 over natural log of k to the k, all to the 1 over k power, which is what? It's 1 over log k. All right? By the way, if you tried to do ratio test on this, I don't think it goes well. Like, I think this is sort of a tailor-made root test problem. What happens as k goes to infinity? The denominator goes to infinity, this whole thing goes to 0. So therefore what? Rho is less than 1, and that implies that the sum 1 over ln k to the k converges. Okay. Anyway, maybe you should work a homework problem or two to sort of make this sink in better. But next time we will start into the next section, which is what? Well, 12.5. What is it? Absolute convergence and conditional convergence. Oh, this is very exciting. This is one of my favorite sections. So, tomorrow. Thanks, guys.